Hello friends, welcome back to this video lecture. Dear friends, from last few lectures we have started to study one of the new important spectroscopy technique, and it is also called as inorganic spectroscopy technique or analytical spectroscopy technique, and the title is ESR spectroscopy or EPR spectroscopy. Okay, we have already seen the long form, that is ESR stands for electron spin resonance spectroscopy. Here in last lecture we have considered about the basic concepts regarding this electron spin resonance. So what is the basic need that can, or which chemical species are able to produce the ESR spectrum, is that they must contain at least an unpaired electron. At least one unpaired electron must be present in that chemical species. Such chemical species are known as paramagnetic species. Then and then that chemical species, either it is free radical or metal ions, okay, or complexes, they are able to produce the ESR spectrum. Here our today's topic is ESR transitions. Okay, so the ESR transitions are possible, or we see how these ESR transitions are produced or they are formed in the ESR spectrum. We know that in last lecture we have seen that the moving electron having a charge can generate magnetic field around itself. Okay, so as electron is a charged particle, and when any charged particle is under motion, okay, when it is rotates, when it is moves, then it is producing magnetic field, and that magnetic field has its own magnetic moment. In other words, the strength of that magnetic field produced by that tiny magnet electron, because that electron is acting as a tiny bar magnet because it is carrying a charge and it is moving. Okay, so the strength of that magnetic field produced by that tiny bar magnet, that is electron, is expressed in terms of magnetic moment. And when the electron is in free state, or if that electron is not placed in an external applied magnetic field, then the magnetic field or the magnetic moment of that electron, due to the spin motion, is randomly oriented. Okay, so as electron having two motions, that is spin motion as well as orbital motion. Yesterday we have seen that the contribution of the magnetic moment, angular magnetic moment, due to the orbital motion of that electron is very less, and in most of the cases, that is in 99.99%, it is the contribution of only the spin angular momentum of that electron. Now this spin angular momentum, that is magnetic moment of electron due to the spin motion of that electron, is randomly oriented in absence of magnetic field. Now what will happen if that such unpaired electron is placed in an externally applied magnetic field? So this is the case here. So this direction, this arrow is indicating that B. So this B is nothing but it is the external applied magnetic field. And when we are applying magnetic field externally, the originally present magnetic moments of that electron, they tend to align themselves either in the direction of the magnetic field or opposite to that of the direction of magnetic field. So these are the two cases. Okay, so if this is the direction of applied magnetic field, if this is the direction of applied magnetic field in the upward direction, okay, then the magnetic moments of that electron having unpaired electron tend to align itself in these either in two directions, along the direction of the applied magnetic field or opposite to the direction of the applied magnetic field. This is the situation, okay, and these two situations, these two possibilities are depicted in this figure, okay. So here what are these two possible orientations of an electron spin magnetic moment in external applied magnetic field, okay. So this is the case, okay, and here this is the magnetic moment mu of that electron due to the orientation of that magnetic moment in the direction of that magnetic field, okay, and it is denoted by plus 1/2 h, okay, and this is the magnetic moment mu, which is orienting in the opposite direction to that of the magnetic field, okay. So this is the situation of the magnetic moments of that electron in the applied magnetic field. So this theta is the angle between the magnetic moment mu and the direction of applied magnetic field B, okay. So the separation between two spin energy levels, the potential energy responsible for this is given by E is equal to minus mu B cos theta, okay. So mu is magnetic moment, B is strength of applied magnetic field, and cos theta is the angle between these two, okay. Now for S is equal to 1/2, for total spin S is equal to 1/2, this situation can be treated like this, okay. So this is the case. Here the energy is plotted on the y-axis. Here energy 0 means we can say that both the electronic state, both the magnetic moments are degenerate, or they are having same energy, okay. So ms is equal to plus minus 1/2. This is in absence of magnetic field. This is the situation what we called in absence of magnetic field, okay. As soon as we are applying externally magnetic field, then these two spin states splits into two, okay, into ms is equal to minus 1/2, it is called beta spin, and ms is equal to plus 1/2, it is called alpha spin. This energy difference between these two spin states is given by the formula delta E is equal to G Bohr magneton of electron into field strength B, okay. So how it is obtained? It is obtained by this equation, delta E is equal to h nu, okay. This is the simple relation, delta E is equal to h nu is equal to G beta E B, okay. So beta E is nothing but the Bohr magneton of that electron, okay. So rearranging this equation, we can get nu is equal to G beta E B upon H. So by putting the values of all these figures, taking G is equal to approximately 2.0, BE is taking 9.27 into 10 raised to minus 24 joule per Tesla, and beta is taking 0.34 Tesla, okay, and H is Planck's constant. The frequency nu for ESR transition comes 9.518 gigahertz. So this is in the microwave region. So that's why in ESR spectroscopy we are using microwave radiations. And when microwave radiations of the frequency in the range of this, when irradiated as a source of electromagnetic radiations to the unpaired electron, when it is kept in an externally applied magnetic field, then the splitting of that spin states takes place and it splits into two energy states. So when that magnetic radiation, that is microwave radiation, if it is having the energy in the range of delta E is equal to G beta E B, okay, then we can say that resonance will happen. Okay, our title is electron spin resonance. So the spin resonance phenomenon will occur and absorption of that microwave radiation will take place and our electron goes to the higher electronic energy state. Okay, so this is the phenomenon that we called ESR spectroscopy. Okay, and this is delta E is equal to G beta E B. This energy difference must be equal to the energy of that irradiated microwave radiation that is used in the ESR experiment. Okay, now the next point is selection rules. So what are the selection rules? There are basically two selection rules for the ESR spectroscopy. First one is the energy of electromagnetic radiation, as we have discussed here. The energy of electromagnetic radiation must corresponds to the energy difference between the energy levels of the molecule. And the second is the oscillating magnetic dipole of the electromagnetic radiation must interact with the magnetic dipole in molecule. Means what? The two magnetic moments, one is of that of electromagnetic radiation, it must interact, then and then the spin resonance can happen. It must interact with the magnetic dipole moment of the molecule. So when such two interactions taken place, then and then ESR spectrum will form. Okay, now the G factor. So what is the G factor? Yesterday we have seen the value of G. It is approximately 2.0 and it is unitless quantity. This G factor is nothing but it is the value which is obtained for an unpaired electron, for an single unpaired electron. And when the ESR signals, when the ESR spectrum is giving signals away from or it is other than this value, then we can say that the shift in the G value can be possible, or shift in the G value can be obtained, and hence this G value is very similar to that of the chemical shift in the nuclear magnetic resonance, that is NMR spectroscopy. Okay, so the significance of this G factor is it is similar quantity, it is unitless quantity to that of the chemical shift in nuclear magnetic resonance spectroscopy. Okay, now the next point is presentation of spectra. So the spectra, electronic spectra or ESR spectrum can be presented as, or can be plotted as a intensity of signal versus strength of magnetic field. Intensity of signal versus strength of magnetic field. Generally, the absorbance peaks for this ESR spectrum obtained are very broad in nature. They are obtained in very broad nature. Okay, so it is very difficult to measure these values experimentally also, and hence to minimize our measurement, or to minimize our errors for the measurement of that ESR signals, it is generally advised that the first derivative of these absorption peaks are to be measured. First derivative means the slopes. First derivative means the slopes of these curves, absorption curves, have to be measured on the ESR spectrum. Okay, and then the first derivative, that is slopes of these absorption peaks, gives a sharp lines or sharp peaks. Okay, and this is shown in this graph. So this graph is showing the signal versus magnetic field graph, okay, for the ESR spectrum. The upper portion is showing absorption peak in the ESR spectrum, okay, and this is shown that here it is shown that the broadness of the signal, or the signal is very broad, okay, and due to the broad signal it is very difficult to measure the exact frequency of that absorbed radiation, okay, and hence it is advised that the first derivative or the slope of that absorption curve is taken, and the first derivative curves are sharp in nature, and hence nowadays the ESR spectrums are shown, or they are presented in the similar way to that of the first derivative of the absorption curves. Okay, so this is all about the how the ESR transitions takes place, then what are the different selection rules, how that magnetic moment is get splitted in the presence of magnetic field, and how that ESR spectrum is get presented in the actual electron spin resonance spectrum. Okay, so this is all about the today's lecture. Okay, thanks for watching this video. Have a nice day.